Hello, good afternoon. This is the Eurovent expert webinar on molecular filters organized by the Eurovent product group Filters. My name is Marc Schmidt. I'm the Vice President Technologies at American Air Filters here in Europe, and I serve as the chairman of the Eurovent product group Filters. What is Eurovent? Eurovent is a European not-for-profit organization bringing together manufacturers from various sectors of the HVAC-R industry. Its mission is to foster energy efficient and sustainable HVAC-R technologies with holistic consideration of other aspects such as health and life protection, quality of work, safety, and the promotion of a level playing field for the entire industry. The Eurovent product group Filters or air filters covers air filters and its related products. It often acts in cooperation with specialist European product groups that cover products which integrate air filters. Before we start, some practical things you see on your screen on the top. It might look a little bit different depending on your operation system. You see different symbols. You see here the gear sign under the number 1. So please mute your microphone. We are more than 200 people here in that call. If you want to ask questions, you can do that at any time. You have to click here the question mark icon. These questions are collected and then handled in the last part of that webinar. And the program handout can be downloaded here under that paperclip sign. And the webinar will be recorded and shared afterwards. So if you are registered, you will receive from Eurovent an email tomorrow with the download link. Today's roadmap. So after the introduction, we are starting with the first questions. Why use gas phase filtration? That's the base questions. And then it's getting technical. Particle filtration, particle filters versus molecular filters will be discussed. Then it's about molecular air filter classifications, and then the most practical part is the selection of molecular filters, and we will end up with a Q&A session. The key learning points for today is to understand why gas phase filtration matters for indoor air quality, to recognize the differences between particle and molecular filtration, to learn how molecular filters are classified according to ISO 10121-3, and to apply Eurovent guidance to select the right molecular filters. The experts we are having here today are these three handsome guys. It's Mr. Karsten Howe from company TROX. It's Tobias Zimmer from company Camfil, and it's Thomas Caesar from company Freudenberg. So let's get started right away with the questions, why use gas phase filtration? So Karsten, the stage is yours.
Are muted.
Sorry. Yeah, thanks very much, Marc, for the short introduction. My name is Karsten Howe. I'm the product manager for filter elements at TROX SE, and I will start with the topic, why use gas filtration? What do we need for good indoor air quality? In the past, the focus were mostly only on particle filtration. So it means, I think everyone knows about the common filter classes, the old one, the F classes we don't use anymore, and also the EPM10, EPM1 classes and something like that. So why do we use gas filtration? Particle filtration on its own is not enough. 90% of our time we spend indoors, and as I said before, historically we're the most focused on particle filtration. But gas phase filtration becomes more and more important due to health concerns and experience with hazards of naturally occurring substances. So gas phase cleaning was only used in cases of odor and nuisance in the past. So everyone knows it when smell something. A lot of guys know it from an airport or something like that, where we use a gas filtration. Most of the times it was only doing odor, but it goes further. And it is essential to prevent harmful substances from entering the interior with the outside air in order to protect people. And this is the plan of the current standard we were talking about. So most of the time, always the question is when we are talking about gas filtration, where does the pollutants come from? So ozone is one of the most important particles. We have no direct source of emission. It's the natural occurrences and degradation products. For nitrogen dioxide, we have the consequence of combustion process. Then the other substance is the combustion of fossil fuels with a higher sulfur content, the sulfur dioxide, and the toluol is representative of the large group of the VOCs, so for the smell things. Where does this comes from? Why do we talking about these gases? These are part of the ISO 10121-3 that you see here, and they are also examples for other different substances. Then why do we use it? Of course, it's health effect. Here we can see the current World Health Organization limits with short and long-term effects on human health. What is important when you see these doses, you can also see these doses in our Eurovent recommendation, is the averaging time. You can see here for O3, we have the peak season and the 8-hour dose. For example, for the NO2, you have an annual average time and the 24-hour dose. And this varies from substance to substances. After this, we come to the next topic, particle filters versus molecular filters. Where are the difference, or why do we use the difference? Of course, we need to filter, we need to separate both from the indoor air. Particle filtration is separation of aerosols, increasing, and the other topics are when we do particle filtration, we have an increase in filtration efficiency over time. So if the filter gets older, pressure drops rising, and most of the time we have also a higher filtration efficiency. We have the particle retention in the filter medium. So that is when we're talking about depth filtration. So it means the particles are inside the filter media. And we have a formation of a filter cake when we are talking about surface filters. Gas filtration is different. So we have two filter parts which are pretty or hard to compare. Gas filtration, of course, separation of gases. You have a reduction in filtration efficiency over time. And what is also, you have the pressure loss remains most of the time constant. Of course, not totally when you have some particles inside or you have some water. When the humidity is high, it gets into the filter. But these are a little bit different. So you can't look at the gas phase filtration like on the particle filters when it's time to change our filters. But this will tell you my colleagues in the next slides. Yeah, then a little bit theory, mode of action of activated carbon. We are talking about adsorption, not absorption. These are the difference when we are talking about absorption is the process of adhesion to the surface of a solid through physical process. So it gets a penetration into the carbon. This means a pre-filter is necessary to prevent clogging the carbon with some aerosols, which we don't want to have. Absorption is only mentioned. We have two types of adsorption. We have the physisorption. It's like for the standard activated carbon with a physical binding forces between pollutant gas and activated carbon. And on the other hand, we have the chemical sorption, which is like for special activated carbons or some other kinds of activating carbons where we have the chemical bonds. What is to tell, you have a high variability for the activated carbon and a significant difference in the separation FNC depending on the medium. So that means there are no single type of coal that is best for all applications. It must be selected based on the specific pollutant, and different kinds of coal can also be combined. Last step, which filter can we use? So which type of filters are on the markets, which you can buy from all Eurovent members. We have a wide variety of designs and types. You can see here on the top left the honeycomb filter, which is a activated carbon filter. Then you have compact filter. That means you have combined material, a filter media with the activated carbon layer, also with depleted filter. Then are some other filters like the back filter, where you have also some activated carbon inside, or you have other filters like a filter cartridge, where you don't have the activated carbon combined with a filter media or a particle filter media. So it means you have pellets, loose pellets inside the system. So we have a wide range from cartridges over honeycomb to compact filters. I hope the short slides will tell you something more. Why do we use this? Why do we need this? And what we can do. And now I want to hand over the microphone to Tobias.
Thank you, Karsten. So it's me to continue with this presentation. And basically, I'm Tobias Zimmer. I work for the company Camfil, and I'm responsible for the public affairs. So basically all the standards, but also the association work. And besides that, sustainability and the corporate communication. And my part is to guide you through molecular air filter classifications. And some of you may remember that in the past, there was basically no classification for carbon filters whatsoever. It was kind of black magic. So some expert had to tell you, does it work or does it not work? Which was not easy to dimension it, especially when we're talking about a regular supply air comfort application. But the good thing is that has changed some years ago, and this is one of the main parts that is addressed in the Eurovent 426. There is a new standard, published in 2022, the EN ISO 101-1 Part 3, which gives a classification system for gas filters for outdoor air, so for traditional supply air filters in comfort application. And the big change is that we are not having just curves and you have to interpret them. It really gives you clear classification for a number of gases. And the gases are not chosen just randomly. We just seen them in Karsten's presentation. We have ozone, SO2, NO2, and with toluene, we have a representative for the VOCs, for all the smelling elements you have in the air. And how does it actually work? The core part of this EN ISO is a standardized test with a normalized dose. So what you do for 1 square meter of face area of a filter, you apply a certain amount of gas. So let's say the first step, as you can see on that table, it's 1.5 moles of the gas. If the filter still holds that amount, you continue to quadruple the dose up to 6. Then you have a medium duty, and then again quadruple up to 24 moles per square meter. So you actually have a heavy duty filter. And then based on these results, the filter will be classified. So for instance, a filter class could be NO2, light duty, 85%, which tells you the filter would remove 85% of the NO2 for a certain period of time, as it says, light duty for a limited period of time. So let's see how the classification actually works. And let's have a look at one of this table where you can basically see some test results. You see on the x-axis the normalized dose in mole, and on the epsilon axis you see the efficiency in percent. And then you can see the limits for LD, so 1.5 0.5, limits for MD 6, and limits for HD 24 moles per square meter. Now, if you look at the filter number A, you can see that this filter, let's say this is an NO2 testing here, this filter starts very high. It has an initial efficiency of 95%. You load it until the light duty dose, no big change. You continue loading until medium duty and you see a slight drop. We are approaching the 90% efficiency, but still very high efficiency. So you continue loading the filter until you reach the heavy duty line, 24 moles, and we end around 80%. So what's the efficiency of that filter? Basically, the efficiency is calculated as the integral below the curve, rounded down to a 5% increment. Sounds complicated, but if you look at the curve, it is actually not. We start at 95 and we end at 80. The average must be somewhere between 85 and 90. That's obvious, even without doing a full integral calculation. And as you round down to 5%, you end up with NO2, that's a gas, heavy duty, we reach the heavy duty line, and the average efficiency is 85. So you have an NO2 heavy duty 85. That's basically a result or a level of result you will mainly reach with using cylinders or other masses of carbon. No? So when we look at the second filter, this compact filter, so it's a 2-in-1 compact filter, particle filtration and gas filtration, you would start in the same approach. So as you can see, it starts lower at 85. We load until a light duty dose, still high efficiency. Continue to medium duty. You already reached 80%. And then you can try to load it until the heavy duty. But as we can see here, at some point, the efficiency drops below 50%. And the drop below 50% is before we reach the heavy duty. So this filter is not heavy duty, meaning it's classified as medium duty. That was the last point where it was above 50. Approach is the same. You take the integral between 85 and 80, and that's not difficult to calculate. If you round down, obviously this is a medium duty 80. And if the filter is getting a bit lighter, let's say we have a panel with some carbon, you still follow the same approach. No surprise, less carbon, you start lower. You reach the light duty dose, but before reaching the medium duty, this specific filter would drop below 50%. So this is a light duty filter that we can see right from the curve. Same approach, you take the integral, which is also not difficult in that case. Obviously, it's a 70, including rounding. Meaning we have an NO2 light duty 70. And just to be complete, looking at the last filter, which is honestly not a product to be extremely proud of, but this filter starts in its NO2 efficiency even below 50. So right from the beginning, it's below 50. And before reaching the light duty dose, it drops literally to 0. So how to classify? It didn't qualify as a light duty because it is below 50, at least at one point. So what we have here is basically the classification for everything that doesn't make it to reach a light duty. We have the so-called VLD, very light duty, with an average efficiency of 15%. So just by looking at these numbers, you can quite easily classify the filters and see how good are the different products for that specific gas. Now you know how to classify the filter, but you still don't know what to use. And for that, we have another standard, the 16793/2025, which has been published by end of 2025 and is literally, and when it comes to gas filter requirements, exactly the same as the Eurovent 426, even if Eurovent 426 has been published earlier. So what does it do? What does it do? It bases the gas filter requirements on ISO 101-113. It puts pollutant limits based on WHO guideline. That's exactly the limits that Karsten showed earlier. And then it gives you a recommendation which filter to use in which application. So the process is quite simple, actually. You first define what is your outdoor air. First qualitatively, and As a side note, all the tables you have here are from the new REVA guidebook on air filtration that has just been published, so it's also a brand new source here. So we have the classification qualitatively. ODA 1 means basically the air is clean, so you are below the WHO limits. ODA 2, it's polluted up to 50% above the limits, and ODA 3, pollution more than 50% above the limits. And if we now look specifically at the gas, because that's our topic today, what does it mean? That means basically if you are, for NO2, let's stick to that example, if you are below 10 micrograms per cubic meter, that's the annual limit of WHO, it's ODA 1 gas. If you're up to 15, 2, and above 15, it's ODA 3. Now you know where you are. That's basically the place of your building, the outside air you have. And the second decision is, of course, what kind of supply air do you want to have in the building? Very clean, clean, medium, or not so clean? And that decision has to be made building by building. There is recommendations in the 426. So for instance, a typical application for sub 1 would be a hospital or something like that. Supply air 2 is basically the recommendation for offices, schools, universities, everything that's for permanent presence. Supply air 3, staircases, etc. 4 and 5 is more underground parking, garbage rooms, and other places of less interest. And if you apply that logic now to the gases, you also get limits you shall reach with the gas. So if you want to have a supply air 1, you have to ensure that your supply air has a concentration of less than 2.5 micrograms of NO2. Meaning basically, you will have to reduce the outdoor air concentration equivalently. And not to make it too complicated, the guideline gives clear guidance here, what level of filtration shall be used to reach that level. And you see, we have a percentage number here, and we have this area here was a B behind it, it's where it's required, and the one was an A, it's a recommendation in that standard, telling you you should use, if you have an NO2 problem, sticking to the situation, and you have an office building, so your office building in a big city, ODA 3, supply air 2, you need to remove 80%. You have to do 80% efficiency against NO2. What the standard does not tell you, if it's an LD, MD, or HD 80. But what's obvious, the lower your filter class, an LD needs to be changed more often than an MD, which needs to be changed more often than an HD. And there's two additional comments in the standard explaining how to select it. Number one, of course, we don't only have NO2, you may have NO2 and ozone. First step, you have to select at least the gas that has the highest exceedance. So if you have the biggest problem NO2, then your filtration solution at least needs to address NO2. And the second one, if you select a gas filter, you shall consider a reasonable lifetime. And that's where, of course, you should ask an expert what is the lifetime you could expect in a certain application from an LD, MD, or an HD application. Also there, some examples are given in the Eurovent 426. But having said that, coming to real life examples, I'm going to hand over to my colleague Thomas Caesar, who will take you from there.
Yeah, thank you very much, Tobias. My name is Thomas Caesar. I'm Vice President Global Filter Engineering at Freudenberg Filtration Technologies, and will show you a little bit the practical application. Next slide, please. So, as we have already heard, different filters can have different efficiencies and lifetimes to various different gases. Here's one example of a honeycomb activated carbon filter. And you can see for different gases how different the efficiency and also the capacity of the filters can be. So what you see here is basically when applying constant gas concentration as given in the ISO standard, and measuring the breakthrough over the time of application. So you can see here in this example, for example, on the bottom, there is SO2 with a quite high efficiency and long lifetime. So there is only a small breakthrough after quite some time. When you compare that to NOx, breakthrough is already larger, but also here we have a quite long-lasting filter. But then when you look at other gases like acetaldehyde or N-butane or toluene here, you have a almost instant breakthrough. So it depends very much on what gases we are looking at to select the right filter for that. Next slide, please. So to summarize what Tobias already showed, so basically the classification, here's an example of a wheat bank cassette filter with activated carbon. Challenge gas is the sulfur dioxide. So you run the gas test applying a certain concentration of gas given in the standard for a certain period of time, and you measure the breakthrough curve as Tobias has already shown, and then you use the breakthrough curve to classify the filter in its efficiency for removing the specified gas, and also to define whether it's a medium duty, high duty, low duty, and so on. Next slide, please. So as already Tobias has also shown, here's some more examples. I showed in the first slide that the same filter acts very differently to different gases. The same way different filters act very different to the same type of gas, depending on the adsorbent, on the chemical impregnations on the filter. So there is a wide range of different filters that can be applied to different gases. So here in the example, for example, you see one filter with a deep bed of pellets inside, so quite a large amount of adsorbent, and obviously then also gives a high lifetime and high capacity. But we also see here two examples of wheat bank filters, one with an impregnated activated carbon, specifically impregnated to filter SO2, while on the bottom you see a similar filter with the same amount of carbon, but an unimpregnated carbon, virgin activated carbon. So also here you see quite a difference in the performance against SO2 here in this example. And similar, you would see similar diagrams you could print for various different gases at once. Next slide, please. And here it's just the same diagram to show the one with the impregnated alumina with quite a large amount of pellets inside is giving a quite high capacity to SO2 in this example here. Next slide, please. So to give you a practical example, this here is from a filter application on a German airport where the passenger area is protected from the VOC, or in this case of airport, it's mostly kerosene emissions that are filtered out and protecting the passengers in the departure hall. And in this case, the average concentrations of benzene is 0.08 milligrams per cubic meter, or if you calculate that, 25 ppt, which equals basically to 1.8 kilograms per year for a set of the cartridges that I used here. I will show you a picture later. In this case here, we're using filters which have cartridges, and you have already seen the pictures of cartridges, 16 cartridges installed in a typical filter frame. That is here 1.8 kilograms per year of benzene arriving at this set of 16 cartridges. So quite a large amount of gas that has to be filtered. So when you look at the practical application, it's not a small air handling unit. It's basically a filter house that extends over 3 floors. And we have 14,600 cartridges installed. So quite a massive amount of carbon needed here to filter out the benzene. And it takes only changing these 14,600 cartridges already takes 6 weeks. Volume flow is 2,600 cubic meters per set of these 60 cartridges. So the total flow, when you look at the whole filter system, is 2.4 million cubic meters per year. And the lifetime of the filters in this example here is 2 to 3 years. Next slide, please. So here we can see some pictures of parts of the filter house. So that's not the whole filter house. It's quite huge, and you can see here these sets of 16 cartridges, each one side by side. In total, these 14,600 cartridges installed here to really get rid of the benzene or kerosene contamination of the air coming from the aircraft. Thank you very much. Next slide, Tobias, please.
Okay, Karsten, Tobias, and Thomas, thank you very much for these really interesting insights into the topic. We are coming now to our Q&A session. And I see here we received quite some questions. Let's start with the first one. Are some filters designed to perform both particulate and molecular functions?
Yeah, yes, I can. So yes, of course. So you can see here in Thomas' slide, he also has the V-band combination filters. So the most common filters for this combination are pleated filters, where you have a multi-layer of the normal filter media, let's say it like this, as you know, and some carbon layers, but you have also the back filters with activated carbon, and there are a lot of types. You will have this both particulate and molecular filtration.
But these are always special filters. A
Yes.
Standard filter, molecular filter does not have that. Okay, thank you.
Yes.
The next question, how do you determine which gas is more prevalent in the indoor environment before recommending the type of molecular filters? So we saw that there are different gases, at least in the standard, but in the real world, there are much more gases. So what's the gas I should have a focus on? Who of you wants to answer that? Tobias, you nodded.
Yeah, right. This standard that we presented is basically for the gases that mainly come from the outside. So we have the NO2, which is a typical outside pollution. We've seen the example from Thomas with the kerosene, which of course comes from the airplanes which are outside, obviously. And but if you want to remove indoor gases, so indoor generated gases, then the first step is basically to measure what you have inside. The ones coming from the outside, you can get from public air quality stations. Then you know how high the pollution is. And of course, if you bring the air in, it's logical that the gas will also come in. But anything that's generated inside, you would have to either know the sources inside or ideally measure inside to be sure.
Okay. But for outside gas, there are air quality websites available showing that.
Absolutely. As you can also see in the 426, there is a huge number of public stations which you can access via the European Environmental Agency, and there you can get exactly those data, annual averages, peak season data, 24-hour averages, to really get an understanding of what's the outdoor pollution with gas, with the different gases. And that can be handled via 426. Indoor pollution is a different topic.
Okay, so we're not flying totally blind. We have these websites, and when it's coming to special cases, then I have to measure and assess the special case. Another questions, when selecting a molecular filter, what matters more, the peak efficiency or average lifetime performance? Thomas, that's something for you.
Yeah, I can answer that. So it's basically the average lifetime performance. And this is also what we are measuring in the ISO standard. We are not measuring peak, and peak means the maximum efficiency, which for an activated carbon filter, for an adsorption filter in most of the cases normally is the initial state. So typically the removal efficiency is going down during operation. And so as you know, you don't want to have a filter filtering only at the instant very first moment, but over a certain period of time. Of course, the average over its lifetime is really the controlling factor and the important parameter.
So it's what Tobias said. It's the integral of the concentration over time. So it's the area under the curve, right?
Exactly.
Understood. Understood. In the same directions, what are the key indicators that a molecular filter is saturated and needs replacement? That's for practical life, I think, a quite important question. So who of you wants to answer? Tobias.
Yeah, okay, I can give it a try. So basically, if you know the filter class, if you're talking about a supply air application, you know your filter class according to the new standard, and you know your outdoor air, you can to a certain degree calculate and predict it. If you don't know at least one of it, then the only way is to measure it. And that can be in simple measurements. If you're talking VOC, it's quite simple. As soon as it smells inside and it didn't smell before, then it's obviously saturated, which is an approach that you obviously cannot follow if you're talking about dangerous gases. Yeah? That can only be done for VOCs. The other way to really predict, in general, the life of a molecular filter is to take out one of these cartridges that Thomas just showed. So you would take out one of the cartridges, replace it with a replacement cartridge, send this into a lab, and there you can analyze what's the remaining lifetime of that carbon.
Okay. Okay, so we can measure it. There are for VOCs, for example, are relatively cheap sensors in the market. We can estimate it if we know the concentration outside, more or less, or we have to measure it. Okay, clear. What are there specific gases or VOCs that are currently underestimated in terms of health risk? That's a very wide question. What can we say here?
I think so from my side, yes and no. So as we all know, in the past, we always talked about only particle filtration, or gas phase filtration is also important. So I think the medicine and a lot of things goes further and further. So yeah, it can be that there are gases that are underestimated at the moment, but I think for the most dangerous gases we know at the moment about, there are good rules and good things we can handle them. So that was my opinion about it.
Okay. Knowing that special cases always have to be investigated separately.
Yeah.
Then there are more questions coming in. Does the filtration efficiency change with the flow rate and concentration of various gases? That's also an interesting question.
Yeah, I can take that. Yeah. So as the adsorption is controlled by various steps that are time controlled, so like diffusion, like chemical reactions, the resident time of the gas in the filter is an important parameter, and so that is controlled by the flow rate. So in principle, as faster the flow is, as less time is for diffusion and adsorption, as lower the efficiency is. And also, of course, the concentrations the gas concentrations are influencing the efficiency of the filter.
Okay. There is another question. I think we talked about that already before, but it comes twice, so it's I think an important question. Is there a way to know when the filters need to be replaced? Tobias, maybe you can summarize your answer before.
Yeah, as said, there is different ways. If you know your outdoor air quality and your filter efficiency in terms of LD, MD, whatever, then you can predict it for a supply air application. Otherwise, you have the possibilities to really take out the filter after some time, test it, and to see what is the remaining lifetime. And certainly for less critical gases, you can measure behind the filter, either with a sensor, or if your problem is whatever smell from a restaurant, then you will simply smell it.
Okay, thank you. And there is a question, what is the difference between molecular filter and HEPA filter by the explanation you gave by his performance?
I can take this question. So
Yeah.
we're talking about two completely different filtration things. On the one hand, for the HEPA filtration, we are talking about most of the time solid particles we are separating. So we are talking about particles like for H14, you have 99.995% of the solid particles which you filters or which doesn't come through. And when you're talking about the molecular filter, you are talking about gases. So that means you filter two separate, different, totally different substances. That's why you need, for the one, you need the standard glass fiber, PTFI media, and or synthetic media. And for the other hand, you for the molecular thing, you need this activated carbon or some other high porous substances. So you can't compare it to another. There are two different things. On the one hand, you have the solid filtration with the particles, and on the other hand, you have the gas filtration.
Okay.
So,
thank you. We have another very interesting question. Any suggestions for gas turbine intake application using chemical filters, since the environments are very aggressive? Thomas, is there something for you?
Yeah, here the Eurovent guideline and the standard very much focuses on HVAC and indoor air quality. So recommendations for gas turbines are very different to what we are seeing here, because in a gas turbine, typically it's about corrosion of blades, for example, stuff like that. So it's different gases to look at. When we talk about hot gas corrosion, it might be chlorine. Then we are typically more on the particle filtration, because that is typically coming from salt and sea salt. I would say it depends a lot on the actual situation, where the gas turbine is situated, what gases we have on the outside. And I think the best way would be to talk to one of the filter suppliers and get specific guidance for the specific turbine in the specific environment.
Okay, good. Thank you. I think we have, I see here another questions. Under ISO 10121-3, molecular filters are classified based on efficiency and capacity for specific target gases. How does Eurovent recommend confirming real-life filter lifetime and performance when outdoor air composition varies or seasonally and multiple gases are present simultaneously? Tobias, is there something for you?
Yeah, basically, I can repeat what I said before. You can estimate the lifetime. The efficiency you can predict, basically, but the lifetime of the filter for the specific gases that are classified here are there. But of course, if you have multiple gases and high concentrations of multiple gases, the lifetime of the filter could be affected.
Yeah. And the focus should be on the most important.
Right,
gas.
The clear rule in 16793 is to focus on the gas which was the highest exceedance in percentage of the limit. which is in the utmost cases actually NO2. And sometimes in Southern Europe, you can also have very high ozone values. But there you can predict the efficiency. What you cannot predict, and that's probably meant here, is if you have multiple gases in high concentrations, there will be an effect on the lifetime, because the carbon filter will absorb different gases that will affect the lifetime.
Simultaneously then.
Simultaneously, and of course,
Yeah. Okay, Tobias, thank you very much. I don't see any more questions. So I thank, first of all, I thank the audience here for participating in that webinar. I thank the presenters of today. That was very informative. And I thank the Eurovent Secretariat and the Eurovent guys in Brussels and in Prague for organizing that webinar. Thank you very much and see you next time. Then we close. Thank you.
Thank you.
Thank you.
Goodbye.
See you.
thank you. Bye.
Bye.
Goodbye.